Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. I'm your host, Dr. Frank Summers of the Office of Public Outreach, and it is my pleasure to welcome you here. As you came in, you might have picked up one of our lithographs. Tonight's lithograph is a supernova remnant, the remnant of an explosion of a star. Looks like a nice red bubble. Matter of fact, its nickname is the red bubble. It's supernova remnant 0509, and I think there's actually more to the name of it. But anyways, if you would like to know more about it, turn over on the back and read the text there that our Office of Public Outreach has put there for you. Our speaker tonight will be talking about supernovae, chasing supernovae with Kepler. Marvelous repurposing of a satellite to do all sorts of science. It's really kind of cool, the K2, all the different K2 mission. Upcoming. Now, this has changed, okay? I had a cancellation and I refilled it and I've got new stuff here. So, on November, which is the second Tuesday, the first Tuesday is Election Day. So go vote. Don't come here. Go vote. And on the second Tuesday, whether your party wins or loses, come here and learn about observing with Hubble from scientific idea to published result and everything in between. Okay. Bill Blair said he's having a lot of fun preparing this talk. And if he did really everything in between, it'd probably be a 17-month talk. So I think he'll condense it just a little bit for us. In December, Mark Kamiankowski has volunteered to do his talk on black holes and other dark matters. Two of the most popular topics in astronomy. You won't want to miss this one. And in January, note, it's the third Tuesday. The first Tuesday is New Year's Day, so we're not going to do it then. The second Tuesday happens during the American Astronomical Society meeting, which is the largest astronomical conference of the year. So we're skipping that one, and we're doing it on the third Tuesday. This is a really cool stuff that actually will probably be talked about a lot at the AAS meeting. Initial exoplanet discoveries with TESS. TESS is the Transiting Exoplanet Survey satellite. Brand new discoveries, really cool stuff, and Scott Fleming will be talking about them. All right, so if you want all the details, website, if you go to Hubble site, you'll find us on there. You can use your web browser and search for Hubble Public Talks, and you should find this. We have links to our webcasting. We have links to our past lectures. You can sign up for our email list and get all the information there. Our email are just basically 2 announcements a month. If you can't sign up at the website, you write your name on a piece of paper, hand it to me. I'll make sure you get on there. And again, as always, if you have comments or questions, you can send them to the email address publiclecture@stsci.edu. For those of you who do social media, we're on Facebook, Twitter, YouTube, Instagram. I myself am on those sometimes, if you find that. This is mostly for the web audience, and they can pause it and copy down these addresses. Right. The observatory is not open tonight because it's under repair. Okay. It's actually it looks like it was a reasonable night for it. Oh, somebody's saying, no, not quite. All right. So maybe it wasn't, but it's not open anyways. So you'll have to go to md.spacegrant.org, check out their Friday night open houses. While it's under repair, I'm assuming they're not going to have it. But if you go to that webpage there and check the observatory status, you will be able to find out whether they are doing observing each and every Friday night. We have a special announcement because Space Telescope and NASA are working with the Maryland Institute College of Art, MICA, on a special presentation called Painting the Sky in Gamma Rays, celebrating 10 years of the Fermi Gamma Ray Space Telescope. And there's one thing you can say about MICA. You may not love what they do, but it's never boring, okay? And so MICA is now taking on gamma rays. All right, when is this happening? The bottom half of this advertisement tells you it's on Sunday, October 14th The doors open at 6:30. The show is at 7. All of the artwork and everything has been curated by both artists and astronomers, and the presentation will be by both of them. So it should be an interesting evening. And what you see down here at the bottom is the Baltimore skyline, and above it is the gamma ray all-sky map from Fermi. So gamma rays and mica. All right, if you want to attend that. And now the news from the universe, not for September 2018. I obviously didn't change this slide today, but for October 2018. Our first story tonight, gravitational lensing and buffalo wings. As you all know, I love coming up with interesting titles. So, a few years ago, I ran a visualization wall here in the building. It wasn't this big, but the point of a visualization wall is that you can see lots and lots and lots of pixels. Matter of fact, my visualization wall was the only place in the building that you could see the brand new advanced camera survey images pixel for pixel. So I got to see a lot of the really fresh data straight off the telescope, because people would bring it to my office and they'd look at it. And one of the most amazing images I ever got to see was the original image of this galaxy cluster Abell 1689. This is a massive galaxy cluster, so massive that the mass of the cluster distorts space and produces an effect called gravitational lensing. Okay, so light that passes through that cluster gets stretched and warped and magnified and amplified in strange ways. And you see these streaky, archy things. Let me zoom in on it. Okay, you can see all these strange streaks and arcs. Those are the gravitationally lensed galaxies. Galaxies behind the cluster whose light has been stretched out while it passes through the cluster. And when Mark Postman brought this into my office, we looked at it and we were like floored, because there was gravitational lensing across the entire image, all the way out to the edges. And which really meant that, Hubble is capturing a lot of really great gravitational lensing, but there's still more to see outside of this, beyond Hubble's field of view. And that has been true for a lot of the gravitationally lensed clusters we've looked at. One of the ones we looked at the most often has been Galaxy Cluster Abell 370, okay? And it's really famous because it has the dragon, all right? So this gravitationally lensed arc is actually it's 3 or 5 images of the same galaxy, but all stretched out together in a form that somebody nicknamed the dragon, okay? And that's sort of what made Abell 370 famous. But just like with 1689, we look at it and we see the gravitational lensing there, but we don't get to see what's around it, all the full extent of the gravitational lensing, until a brand new project has come up. And it has a tortured acronym like a lot of astronomy projects. Beyond Ultra Deep Frontier Fields and Legacy Observations. Yes, they got Buffalo together as their acronym. So the Buffalo Survey, which is a project to try and extend out and really get gravitational lensing as well as Hubble can do it, they've looked at Abell 370, and instead of this region, they are taking that much region in. Okay. So this is their first image that they've released from the project, just to say, hey, the project is going and we're getting really good data and we're seeing things. And what we're able to do is look out and see not just the really strong lensing in the center, but as you get further and further out, if you got strong lensing here and you go further out, it becomes weak lensing, right? So you're going from the strong lensing regime toward the weak lensing regime, and we're able to get much better observations and understanding of the distribution of mass in this cluster, which is what gravitational lensing really tells you about, because you can see where the galaxies are, but where is the mass, and in particular the dark matter of the universe? How is that distributed? And so the Buffalo Project will be able to do that on larger scales, giving us finer details and more understanding of the largest collapsed structures in the universe, these giant galaxy clusters. So the joke is, of course, that by looking in the wings, in the buffalo wings of the cluster, we're going to get a lot of new information. Yeah, I'm sorry, I had to do that. All right, our second story for you tonight. Our solar system grows again. Everyone thinks we know all about our solar system. We're still discovering in our solar system because, when people think of the solar system, they think of the sun and the 8 planets, okay? That's the central region of our solar system. We've got, the 4 rocky planets in close, the 4 giant planets out there, and that's your basic picture of the solar system. But if you've been paying attention, you will know that in the 1990s, we started discovering a whole new region of the solar system, and it's called the Kuiper Belt. Okay, and those are the orbits of Jupiter, Saturn, Uranus, and Neptune, and all those red and white dots have been discovered since 1992. Thousands of objects. They're small, icy, with elliptical orbits and tilted orbits, etc. And Pluto is the largest of the Kuiper Belt objects. Okay, sorry, it's not a planet anymore, but it's now the king of the Kuiper Belt. If you want to, feel good about it. Okay, and if you've really been paying attention, you know that the Kuiper Belt isn't it. We also have a region of the solar system that we've never seen directly, but we've sort of seen indirectly. It's the Oort cloud. And this is a logarithmic plot. So you can see the Oort cloud is way, 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 way out. It goes out to like 50,000 AU, whereas the Earth is 1 AU and Neptune is 30 AU, and the Kuiper Belt goes to 50 AU. This goes 1,000 times farther out to 50,000 AU, okay? And this is where the long period comets come from. All right? So there's a lot more to our solar system than you usually think. And we hadn't really gone out beyond the Kuiper Belt, except we found this one strange object in the 90s. Or in the early 2000s. It's called Sedna. Now, up in the top there, you see the orbits of the giant planets, and I think that purple one is the orbit of Pluto. Okay, so Pluto gives you the scale of the Kuiper Belt. You can see Sedna goes way, way, way out. Sedna at its closest is like 75 AU, and it goes all the way out to almost 1,000 AU. What the heck is it doing there? Okay, it's sort of beyond the realm of the Kuiper Belt, but it's inside the realm of the Oort cloud. And it was really hard to understand how you could get an object sitting there. And then we found, hey, you know what? It isn't the only one. All of these objects are, you can see Sedna's orbit here in the dark purple, and all the light purple objects have been discovered, and they have similar objects. We've got half a dozen or so of these objects that are sitting out in sort of a no man's land of the solar system. And that is what caused Mike Brown and his colleagues to hypothesize that there was this actual Planet 9. After getting rid of Pluto as Planet 9, they brought it back as a hypothesis to explain all of these orbits that are out sort of in this no man's land of the solar system. So they have been looking for Planet 9 for a couple years. They proposed this in 2015, and they've got some searches underway. And yesterday, they announced, no, they didn't announce Planet 9, but they announced a new object, 2015 TG387. Now, take a look at this scale. You see Sedna there going out to 1,000 AU? TG, which they call short for the Goblin, TG, because it was discovered around Halloween 3 years ago, goes out to 2,300 AU. The solar system size of what we've observed has just doubled. Yeah. And what's significant about this is starting to get out to the area of the inner edge of the Kuiper Belt. Okay? So TG387 is going out to where sort of the inner edge, but it still comes in and is out sort of well beyond the Kuiper Belt. When they analyzed this, and it took them 3 years, by the way, to get this orbit, okay? They discovered it in 2015. It took them 3 years of follow-up observations in order to determine this orbit because it's moving so bloody slowly, okay? And when they analyzed it, they found it too was consistent with the hypothesis of Planet 9. So they have doubled the size of the object of the orbits of things we've seen in the solar system, and they found yet another object that seems to lend credence to the hypothesis that there is this, several Earth mass type planet out beyond the Kuiper Belt. They haven't discovered that yet. They're still going to keep looking, but hey, Our solar system just got a little bit bigger. We're still discovering things in our own backyard. And on that, how big is the object? The object is about 300 kilometers in diameter as an estimate, okay? It's not well resolved. So it's about 300 kilometers, so it might be spherical. So they actually, in the press release, called it an extreme dwarf planet. I deleted that text from this diagram because I don't think it's justified yet. But it could be a dwarf planet by the AAU's convention. By being 300, it might be spherical, but it might not be at 300 kilometers. So we're not quite sure all of the details of it. But hey, there is still something new under the sun, or at least around the sun. Yes, question.
Do they have a guess at a rocky planet or gaseous?
Okay, so the question is, do they have a guess about what the composition of Planet 9 would be? It would have to be several Earth masses, from what I understand. It's been a while since I've looked at this in detail. But they're looking at several Earth masses, which would be a rocky type planet like Earth. Okay, one more question up there.
Do you have any idea what the periastron would be?
Do I have any idea what the periastron of Planet 9 would be?
Yes.
No. It's not my field. I'm more cosmology, not solar system. So I have to bone up when I do these presentations. But I'm sure if you look up Planet 9 and such, there are several papers available on it that might be able to show you the parameter space that they're looking to try and find this hypothesized object. Okay. All right. And so now we go over to our featured speaker. And our featured speaker tonight is Gautham Narayan. He came to us, he started out, you did your graduate work at Harvard, and then went to NOAO as a postdoc, and then came here as a Barry Lasker Fellow, and is now working in the Science Mission Office here at the Space Telescope Science Institute. And I'm really looking forward to this talk, so let's give him a warm hand. Gautham Narayan.
Can you all hear me okay? Okay. So let's wake this thing up. Maybe. All right. So the title of this talk is Chasing Supernovae with Kepler. But I learned very long ago from Stanley Kubrick that I should always name things after what they actually are about. So this isn't really about chasing supernova with Kepler. It's about how we commandeered an exoplanet telescope to go study stars that will go boom. And that's a much more fun title, I think. This isn't a project that I am doing by myself. There's plenty of people working on it. These are a list of the Kegerators, collaborators on this experiment called KEGS, the Kepler Extragalactic Survey. The PI of the project is Armand Rest, who is a scientist here at Space Telescope and my mentor. And so I'm talking about all of our work really on this project. It's a team effort. It's a great little project that we have. So to begin with, how many of you have heard of Johannes Kepler? Show of hands. All right, a few of you. All right. So let me talk a little bit about the astronomer of the mission to start with. Johannes Kepler was the imperial mathematician in Graz, and he was an assistant to another famous astronomer, Tycho Brahe. He's a contemporary of Galileo Galilei. But he was a smarter man than Galileo for a couple of reasons. The first reason was that Kepler was a very good optical scientist and learned how to make really good telescopes. In fact, we call most astronomical telescopes today Keplerian telescopes. They have two convex lenses, and this was much better than Galileo's design of a convex and a concave lens because it allowed him to measure distances and angular distances very precisely. He could find the separation between two stars on the sky through his telescope much more precisely than anybody else in his day. That led him to be able to make very, very precise measurements of the motion of stars and planets in the sky. He could study these things very, very accurately, and he took very beautiful, detailed measurements of these things, recording them in notebooks. So his observations of the planets, in Mars in particular, allowed him to determine something very important, that their orbits, like you saw for Sedna and the Goblin in that wonderful little talk by Frank, their orbits weren't circles, right? They were elliptical. They were sort of a circle, except you take it and go squish in a direction. And so in his notebook, Kepler was the first person to actually describe this circular motion, this elliptical motion rather, showing you here how a circle looks versus the geometry of an ellipse around it. This is the second reason that Kepler is a smarter man than Galileo. While Galileo was getting in trouble with the church for his heretical teachings, Kepler sensibly added angels to his plots. So that kept him on the good side of things. So, in honor of Kepler's pioneering work, NASA named its big exoplanet flagship mission after him, the Kepler mission. This is the Kepler satellite. You actually walked by a model of this thing as you entered Space Telescope, and as you're heading out, take a look on your left as you're walking out the glass doors, and you'll see it there. It's a beautiful thing, and this entire mission has been incredibly successful. This isn't, of course, the only way we honor Kepler. I named my dog after him as well. This is Kepler the dog. So let me tell you a little bit about how Kepler works. That's the satellite over there going around the sun. And you can see it's oriented in roughly the same direction. It's pointing its solar panels towards the sun at all times. And it's staring in roughly the same direction in space. And it's staring at stars. And it's looking for planets that go around stars. And when a planet does pass in front of a star, what you can see down here is that the brightness of the star drops, right? So this is how bright the star is a function of time. So time is marching this way, and star goes in front, drop, come back. And Kepler is seeing hundreds and thousands of these all the time. These things are called transits. And this particular form of a plot is of brightness versus time is something we'll call a light curve. And I'll come back to why that's important for most of the talk. So this is the Kepler field of view, and it's found in the course of its primary mission several thousands of planets. This is our solar system for scale, and as you can see, most of the systems it's finding look nothing like our solar system. Our solar system's kind of odd. This might be because the Kepler is sort of finding planets that are around hotter stars that are brighter, and also finding bigger planets, but it is still a tremendously successful mission. And it has been really just an incredibly revolutionary tool for our field. But I'm not interested in planets. Like most kids growing up, I was interested in sci-fi. I was interested in Star Wars. I was interested in Star Trek. I loved Superman. And so I was left with this image of what I actually wanted to happen to planets around stars from Superman. Does everybody remember Superman? What planet does Superman come from? Krypton. So Ed Shire, who is an astronomer at UMD, was looking at some planetary system, or what he thought was a planetary system, and something very odd happened. Instead of getting fainter with the planet causing the light of the star to reduce when it goes in front of it, this thing got brighter. And he remembered, he said on this date, this beautiful quote on just how science works. He remembers not knowing whether he should believe it or not. Did I make a mistake? Am I doing this all wrong? This is hardly what Eureka and Archimedes is like, but this is actually how we do science. We doubt ourselves all the time. But Ed was right. What he had found was something that we had known about for a while. It's a supernova. And if you have seen Superman, you recognize this kind of thing. So this is the planet Krypton. And in just a second, you should hear Marlon Brando's soothing voice come over the loudspeakers, telling his son Kal-El that he will always be with him. That's Superman's little cradle shooting off towards Earth. And we're zooming out here from the planet Krypton, and we're seeing why Krypton is doomed and why Superman actually happens. Superman is happening because the planet Krypton is around a giant red star that is going to have something problematic happen. Bounce. That's a supernova. That's one kind of supernova. And as you can see, the planet Krypton is not going to fare so well. Supernovae makes it at least. And believe it or not, that animation is actually pretty accurate. That is actually how quickly a star will collapse. Now, we've known about supernova for a while. Kepler himself found this. This is the intro slide again of the talk. And this is from Kepler's own book. This is from his book called De Stella Nova in Pere Serpentari, the new star in the foot of the serpent, over here with an N. So back on October 9th, 1684, a bunch of Italian astronomers looked up and saw something that they had never seen before. The heavens changed. Literally, this thing that they thought was static and incapable of ever-changing and was perfect, suddenly had a new star in it that they could see with their eyes in day for 3 weeks. They had no idea what this was. What this is a portent? Could this mean something tremendous is going to happen? Kepler, with his telescope, could study this for a year. He collected not just observations on it from himself, but also observations from all of the other astronomers of that time. It's one of our best records of how astronomy was done in the 17th century. And so we know a lot about this star. We know exactly where it is in the sky. We know how bright it was at the time and how its brightness changed as a function of time. We know its light curve. And we can look at it today. And this is what is left of the star that blew up that Kepler saw, among others. This is a composite image. And I'm going to do the CSI thing and hit enhance, which will maybe happen if my computer wakes up. There we are. So this is an enhanced view of the same image, and it has 4 colors telling you different bits of information. The blue and the sort of greenish light are X-ray information from the Chandra Space Telescope. These are hot, highly energetic particles, X-rays shooting out at us. The green is slightly lower energy. The yellow areas are what we see in the visible. This is with the Hubble Space Telescope, where we see gas and dust left over from the explosion, lit up by a shock wave that ripped through this entire star. And finally, the red is where the shock wave is today. This is where the dust is imaged by the Spitzer Space Telescope. So this is a really amazing picture. You can see this image of a star that blew up in Hollywood, and we can actually look at these things today and find them in the sky. And they're really important because if you've ever looked at the periodic table of elements, outside of hydrogen and helium, which are produced in the Big Bang, pretty much everything else down here is from a star. So when you hear somebody like Carl Sagan say, "You are made of star stuff," this is what he means. Every calcium atom in your teeth is from an exploding star. That's something cool that you should remember. Now, supernovae are amazingly bright things. This is a galaxy, and if you look down here, you'll see a supernova get brighter over time and fade away. This is its light curve again, and you can sort of see they last for around 30 days. And you can see them easily with a telescope like Hubble. But I want you to take a step back and get the big picture here. This is a galaxy with something like 10 to 100 billion stars. And this one supernova was still so bright that you could see it against all of that. That's pretty cool. The problem, of course, is that they are kind of rare. So in a galaxy with 10 to 100 billion stars, you can still only expect a supernova, 1 or 2 supernova, every 100 years or so. So to find these things, you've got to look at lots and lots of galaxies. Now, the Kepler mission was, of course, looking for exoplanets. It was staring at one little patch of sky, a little larger than the full moon, and it was continuously looking at that region of sky for several years. But because it's a small region of sky, because there are relatively few galaxies in there, you're not going to find a whole lot of supernova, right? That makes sense? But we are going to get lucky every now and then, so we did find some. There were about 6 supernovae that we found from 2010 to 2012 with Kepler, just fortuitously. The kind of supernovae that I care about are type 1a supernovae, and that's just sort of the examples of what you're seeing here. Oops. So you see nothing, 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 explosion happens, and suddenly there's a bright increase in the amount of light from this supernova. the Kepler data is spectacular in many ways. From the ground, we can expect typically about 40 observations of a supernova over its entire 30 days lifetime. What we get with Kepler is something like 4,000 observations over its entire lifetime. That's just way more data. And in particular, that's really useful because it lets you study just these sort of areas right before when the explosion happens and as the explosion's happening. That's an area we almost can never study from the ground because we can simply never take enough images of it from ground-based telescopes. So we found several different kinds of these supernovae, and we've seen interesting physics from them. We've seen, for example, a shock break out of the star like you saw in that Hollywood movie and rip apart this thing. And this is something we've just never been able to do until Kepler. But of course, the challenge is still there. We're only going to find a few of these things. So here's a couple of interesting light curves that we've seen from Kepler. Here's this little bump that I talked about. That's the shock breakout. This is a star exploding. Nothing, nothing, nothing. Boop, explosion. Finally breaking out of the layer of the star. And we just can't do this from the ground. So we really want some way of hijacking Kepler, commandeering Kepler, stopping it from doing exoplanet science, and doing all supernova science, because this is just tremendous. This data is invaluable for us, but unfortunately, the exoplanet people want this thing. And then something horrible happened. Just as things were getting interesting, the wheels came off Kepler. This was the headline. One of the reaction wheels that kept the spacecraft pointing in the right direction failed. Suddenly, it needs 3 of these things for yaw, pitch, and roll. Suddenly, it had to keep spinning in one direction. That's a problem. That means it no longer can stay pointed to look for exoplanets all the time. But that's also not really good for finding supernovae, of course. So we were, kind of like that. And this kind of answers the question. Murphy's law is greater than Kepler's law, right? But this is NASA we're talking about. This is the agency that, goes with failure is not an option. And so we have the best boffins there are. And because we have the best boffins that are, we came up with a cool solution for this. This is just the coolest thing. In place of a failed reaction wheel, we're using sunlight to balance the spacecraft's rotation. So the sunlight exerts a small amount of pressure. If it's unbalanced, it can spin that spacecraft. But if it's perfectly balanced, the spacecraft will stay in the same location, despite its lack of that third reaction wheel. So if you point Kepler just right, you can still do observations with it with only 2 reaction wheels, with only this 2 gyro mode. And this is not ideal if you're looking for exoplanets. You're losing so much precision and the ability to stay pointed exactly on stars. But it's great if you want to find supernovae. So we finally got rid of those exoplanet people, and we're like, yes, we can totally do this. And so we call this new mission K2, the second light effectively for K2. And now we can get these exquisite 30-minute cadence light curves, observations every 30 minutes over 100 square degree field of view. And we're no longer looking at just one patch of sky, but we can look at something like 2,000 to 14,000 galaxies every 80-day campaign with Kepler's K2 mission. So suddenly, we go from having a small number of supernova to be able to finding a lot more supernova. This is what really happened, right? This is the one patch of sky Kepler was looking at where we couldn't find a whole bunch of supernova, and suddenly now we're allowed to look at a whole range of sky. That's much way better for us. And this is great because on the same sort of scale, here's the kind of number of supernova we expect to see because we've been following these with other telescopes. This is every supernova that's happened in about the last 400 years, in 1691, in about 15 seconds. There's a lot of these things if you look at large enough parts of the sky. That's cool. And so we can find a whole bunch of the supernova simply because we're now looking over a larger search area. This is really tremendously useful for us. And so we can start to do supernova science with Kepler. Now, the kinds of supernova I care about aren't like that collapsing giant star that I showed you, but are rather what happens when a small remnant, a burnt-out remnant of a star called a white dwarf explodes. And it does that in 2 different ways. It can either steal matter from another companion star over here, or two of these white dwarfs can get ever closer to each other, spin, and then merge, and then they explode once they hit a certain amount of mass, where gravity can no longer balance sort of internal forces it has. And there are different, so these are the two sort of progenitor channels of making a type 1a supernova, the kind of thing that I care about. And then there's also different kinds of physics that you might expect. So you start off with a white dwarf and something else, and then somehow or the other you put in some explosion physics over here, and then you get this thing that blows up called a supernova, and you can study all the chemical elements that come out of it from the periodic table. And this lets you really, if you can study all of this stuff with Kepler, you can really get a handle on exactly what this question mark is. What's blowing up over here? That's the real question we want to ask. What's the physics of these explosions? And so there are different explosion models. Some of these things we think grow to roughly around 1.4 times the mass of our sun and then ignite near the center. Some of these things we think just sort of have a burst near the explosion, near the surface. And some of these things we think get super heavy and then become much more energetic explosions. And in a very, despite the fact that the physics here is very different than that Hollywood movie, these explosion simulations have much the same result. The entire star blows up in a few seconds. If you sort of made a grid of all of those models, different kinds of progenitor scenarios plus different kinds of explosion models, there's a lot of different options out here. I don't want you to try to read all of these. What I want you to take away is we actually have no good idea what is causing these explosions, and what we want to find is which box here is actually producing these stars. This is what we want to identify. And there's lots and lots of different options for these things. So when we study these things from the ground, we can find lots and lots of supernova of different kinds. So we really want to find for each one of these groups, is there a separate explosion mechanism that's responsible? Is that circle with a question mark different in each of these cases? Are they the same? Are there different contributions to each of them? And we've simply not really been able to do that so far easily from the ground. It's just been too hard because we're not studying supernova early enough. We have some idea of what might happen and some ways to distinguish these models. Back in 2010, Dan Kaysen said, who's an astronomer at UC Berkeley, said that if you have a white dwarf blowing up near some star like our sun, what you should see at really early times where Kepler can look and other things can't is an excessive flux, an excessive brightness from material from that white dwarf running into the companion star, lighting it up. So now that gives us a way of disentangling these different progenitor scenarios from each other. We can potentially differentiate these things if we can look at light curves early enough, which again, we can really only do with Kepler. Meanwhile, back on Earth, we're getting a little better at doing this, and so we're getting more and more confident that some of this picture is right. We've started to find supernovae where we have some limits on what these explosion scenarios can be. So this is an image of 2011 FE, which is a supernova. And we know from deep Hubble imaging here that there's no companion that's larger than a single solar mass, right? So there's nothing that looks like a big star near a white dwarf in this case. That's already one little piece of evidence that suggests something is going on, and maybe it's one scenario and not the other. We've seen a few others. We've seen cases where there does look like there's something at the site of the explosion before the star blew up. So here's the supernova that's happening in this case for 2012Z. And here's the site of the explosion. You could see something faint and fuzzy over here. So we know that there's something there, but we're not sure what it is. There's some other supernova that we've seen, these sort of UV excesses in, we think, but you can look at how ratty this ground-based data is compared to that beautiful Kepler data I showed you. There's almost so much noise over here, we can't be sure if this is just a random spike or if this is actually a signal of that excess. And finally, we've started to see new things this past year where, again, this is 2012Z, oops, skip through that. Where right at early times, there's a slight bump over here, and it's a slight bump that might say that there's some kind of companion over here. So for me, trying to understand what the physics of these progenitor systems is, These are all tantalizing clues, but they're not smoking gun. So now with Kepler back in business, with reaction wheel fixed effectively by using the sun, we can go hunt type 1a supernovae, right? The first thing we found didn't look anything like a type 1a supernova. That's a regular type 1a supernova up here in blue. And what we found was something that did this, way different than that. And we were like, who ordered this? Armand Rest, who's in this building, led the analysis of this. And it's a supernova. It's in a galaxy. There was nothing there before, and then suddenly it pops up and disappears. And it does that in 14 days. It's very inconsistent with all the other supernovae we've seen. It's also inconsistent with all the other things that that we know that sort of rise up and have relatively short time scales that we've seen. So the picture we've come up with for this thing is that it's a star that near the end of its life sort of had a burp, sort of belched out a bunch of gas, and then right before the explosion, it did this, and then the explosion happens, and it runs into all this material that it's burped out. That's lit it up. So Kepler is now teaching us things about exploding stars that we just didn't even imagine we'd learn about initially. We never imagined something like this thing, like KSN 2015N. It was just something that happened to be discovered fortuitously with this experiment. But now we really want to find the things that we did imagine, right? We want to find the kind of type 1a supernova that I've sort of started this talk telling you about. And Kepler has effectively broken up the K2 mission into several sort of 80-day campaigns. The vast majority of these campaigns, the orientation of Kepler with the Earth and the Sun is exactly how I showed you in that original movie of it going around and pointing in the same direction, just at one of these fields. For campaigns 16 and 17, they did something rather different. They flipped the telescope the other direction. That's really useful for us because for all the other campaigns, we've only had a very short window right around twilight where we could see something with the ground that Kepler could also see. But by flipping the telescope over the other direction, in this lovely cartoon, suddenly the Earth and Kepler can both observe the same patch of sky at the same time. And so here in this beautiful illustration, Kepler says, hey, Earth, give me some spectra. And people on Earth, us, can go point our spectra at this. And so for most of last year, this is what Armin and I and all of the other people on this project were involved in, hunting supernova that Kepler discovered from the ground, seeing if we could get more additional information about it and realizing what it was soon. And so campaign 16 and 17 were focused on these extragalactic transients, and it suddenly became like Christmas. We had been finding, 6, 10 supernova. We found 42 in campaign 16 and 17 put together. It's just a tremendous explosion of these things. Suddenly a whole bunch more data for us to work with, lots more papers to write, lots more analysis to do. And so what we did was coordinated follow-up with many, many different telescopes. The Pan-STARRS telescope in Hawaii, the DECCAM instrument down in Chile, along with SWOPE, small telescopes called the Atlas telescopes that are designed to actually provide a warning if an asteroid is headed towards Earth, a whole bunch of different facilities. All of these things were coordinated, observing the same patch of sky that Kepler was observing at once. This is actually kind of unprecedented. It's hard to get a whole bunch of scientists in the same room and get them to agree about anything, let alone to dedicate their resources towards doing the same science. So this is really sort of a model for how to manage follow-up with scarce resources like Hubble in the future. And we found interesting things. So this was one of our interesting objects. This is supernova 2018 OH. It's a regular type 1a supernova. And it was discovered by the Assassin survey on the ground, and it was in the Kepler field. And here is an image of that supernova. And if I click this, you'll see this animation. And near the center here, you should see this thing get brighter and brighter over time. That's why the supernova is. That's what Kepler is seeing. And we can follow it with other instruments from the ground and compare it with all sorts of other type 1a supernova at the same time. And so we can finally say, hey, this thing looks a lot like other supernova or doesn't. We can find the differences. And we can look at these things really early because we have this great Kepler light curve. So if I flip to this great Kepler light curve, here's our sort of 4,000 observations across the light curve. Those are individual little measurements in gray, okay? Every one of those is an image Kepler took. If we average them together in bins, those are the black points. But the great things are our actual data, and this is tremendous because you can look at this and look for very, very minute differences, very, very minute departures from theory. The theory here is what the red line is, and you can see the observations depart just a little bit from it. But that's the signal. That really subtle, small departure is the signal that we're looking for. This is one of these potential smoking guns of that this supernova is not a simple system that is simply two white dwarfs near each other. This looks like the sort of excess we'd see if a supernova happened when a white dwarf is near a star like our sun. And so this is starting to look really good because now we have clean data that's a lot more convincing. We can correct our supernova, compare it against everything else that we'd seen from Kepler in the past, and the signal still persists. There's just no way this flux excess could have been not detected in those previous supernova had it been there. So this thing is genuinely different than the previous supernova that even Kepler had seen. And so the question now is what the source of this excess flux is. What is the physics of the explosion? And so we can rule out a whole bunch of models, but the four that remain are collision with a binary companion, a star like our sun, or it could be the mixing of nickel, which is produced during the explosion of a supernova right on its surface, or it could be interaction like you saw in that burp where the star has given off a whole bunch of material right before it explodes, and it's interacting with that material, lighting it up. Or it could be two of these stars hitting each other and blowing up all at once. And so those are the four explanations we were trying to sort of consider in a set of papers. Some of them fit the data better than others. And so the two sort of leading models right now that we have are this collision model where a supernova is running into another main sequence star and lighting something up, or the surface nickel model, which we can't really rule out with what data we have from just Kepler. But we have more data than just Kepler, of course, because we can follow it up from the ground. And so we can look for colors, and we can sort of look and see which models are supported. And based on this, my sort of preference here is that this is sort of more close to the collision model than any of the others. There's still some debate between the surface nickel team and the collision team, but we've narrowed down that grid of possible models from several different options to two. That's a whole lot of improvement over what we've had in the past from just one object. There are other objects that we're going to work on soon too. This is 2018 AGK, another supernova that we've seen. This is not perfectly reduced yet, but it seems to have the same little excess of flux down here that we think might signify that this too is a star, is a white dwarf star around a star like our sun that's blowing up. And teasing out this really small signature is going to be work for the next few months for me. We're still working on sort of removing these artifacts and signatures in the data, and some of these actually come from how Kepler observes. I told you we were balancing this thing out effectively with sunlight, and that doesn't work perfectly. If you actually look at a star with Kepler, it bounces around because the solar pressure is not constant over time, and you can see all sorts of instrumental artifacts. You can see a little asteroid or something move through the frame over here. You can see cosmic rays. All of these complex effects all have to be accounted for in the data when we analyze things with Kepler. But while this is a complicated problem, teasing out these delicate signals from the data is something we can do and something we're getting better and better with doing. But here is where the happy story sort of comes to an end a little bit. Kepler is dying. It's running out of fuel. It's on its last legs. This will almost certainly be its last campaign 20. And it probably will not finish it. They will have to probably stop taking observations and save the data from the telescope before it runs out of fuel. But the good news is that we have more telescopes on the way. This is sort of a timeline, effectively, of NASA's exoplanet telescopes. And Kepler's over here, but it's already been succeeded by TESS, which is the next great exoplanet mission from NASA. And it's going to be followed by the Webb telescope, a model of which is over there. And in the future, sort of in 2025-ish, WFIRST mission. And TESS is an incredible thing. Where Kepler was staring at a small patch of sky at a given amount of time, in 2 years, TESS will cover the entire sky with really high cadence. That's pretty impressive. it doesn't go nearly as deep as Kepler. We can't see as far out into our universe as we do, but simply because of the amount of area it covers at any time, it will effectively be a machine at finding these supernovae. And so we'll go from probably a handful of objects where we can tease out the signal and understand the physics of the supernova to hundreds of these things. And so we expect we'll also find things that we've just not imagined before in the data. And that'll be kind of an exciting time. So I sort of want to wrap things up a little bit and take questions from you folks. Kepler has been a really amazing facility for us. We've been finding all sorts of things that blow up, stuff that effectively made me an astronomer and lit up my eyes as a kid, all of these exciting explosions. We've seen these excess flux in a couple of objects. We've seen other objects that don't have it. We've seen things that we just didn't imagine. This, for example, is a light curve for an object my student is working on, and its entire time scale is about 20 days. It rises and falls much, much faster than a supernova, and we know nothing like it. We've never seen anything that behaves like this. It's just a mystery as to what it is. That's just cool. It's discovery space for us. We're learning about explosions that Kepler himself could never have imagined, but these things are so rare that he never would have seen them. And we're finding things earlier and earlier than we've ever managed to before. Along with experiments like LIGO, which understand not just photons, but gravitational waves, and ice cubes that are studying neutrinos, we're really learning about things across the entire electromagnetic spectrum. We're no longer just looking at the sort of beautiful visible light images like this Hubble picture that you got at the Bubble Nebula, right, when you walked in. And this is really cool because what will happen is that we'll understand the progenitor systems and physics of these supernovae, which will in turn help us understand and explain and improve our models of supernova better. And so in a few years, if you come back here, I hope to not have any of these question marks on our slides anymore. I hope to not have any circles where we don't understand what the origin of a particular star's explosion is. I hope we'll be able to fill that entire thing out and tell you, here is how this star lived, here is how this star died. And there's more to come because there's so many more exciting missions in the near future. And with that, I'll take questions.
All right. Do we have the microphone cube coming down? Yes, the microphone cube is coming down. All right, who's got a question for us? You can do it without the microphone cube. I'll repeat it.
When these supernovas happen, blow up, what happens after that?
When these supernovas blow up, what happens after that?
Does it become like a platform for other stars to form, or is it just like a pedal in a stream ahead, and then it just dissipates? What happens?
This is a beautiful question. So if you look at that image of the Bubble Nebula that you got as you walked in, that's what remains from a supernova. Actually, can you pull me one of those, Frank? Sure. Just to hold up one of these. This is kind of what it looks like for a supernova several hundreds of years after the explosions happened. And so what you have is this smorgasbord of material that was produced in the explosion of the stars, all the heavy elements, all the way up to iron in the periodic table. And it's absolutely true that supernovae are destructive forces. If there were planets around that star when it blew up, they aren't there anymore. But on the other hand, they are also creative forces. Because these things are effectively engines producing the periodic table, you're absolutely right. They enrich the galaxies. They enrich their surrounding environment. The next generation of stars that will be formed will incorporate material from these supernovae. They will have more metal, for example, than stars like our sun, which are composed mostly of hydrogen. They'll have slightly different properties. And this is effectively the universe recycling a little bit.
Let's let the wife of the speaker ask her question.
Oh dear.
Have you thought about the type of explosion that our sun will have?
Yeah,
Have you thought about the type of explosion our sun will have?
So a star like our sun is not going to have an explosive fiery death. It's a little bit more wimpy. It's going to sort of puff up and become a red giant star. its size will be a little less than the orbit of Jupiter, so all the inner planets will be cooked, but this will be in about 5 billion years. You don't have to worry about your property values. And once that puffy red giant phase is over, what's left at the center of the star is its core, this white dwarf, the sort of thing that becomes a supernova of type 1a, potentially. That white dwarf, if nothing happens to it, if it sits there by itself, it will simply cool for the rest of the lifetime of the universe. When interesting things happen is when that white dwarf starts to get mass from some other companion, whether another star or another white dwarf. And that's exactly the kind of scenario we're trying to figure out.
Okay, other questions? Yes, in the center there. Here, catch it. Catch the microphone. There we go.
16 and 17, you pointed the Kepler the other direction and coordinated with Earth and, God, I don't know, 7 or 8 more times observations of supernova. Is that because of the coordination with Earth or because it was pointing the other way?
Exactly. So the question was, did we find more of these supernova because we were pointing the telescope in the other direction? The answer is exactly yes. When it's forward-facing in the configuration I showed you, there's only a short window around twilight, morning and evening twilight, when observers on the ground can look at the same area of the sky that Kepler is looking. After that, the field sets, and so it's below the horizon. We can't go point our telescopes at it at night. That doesn't make for a very large window with which to go find supernovae. When you do it in the opposite geometry, then suddenly the field that Kepler is pointing at is also available to be observed from the ground for basically the entire time it's dark. And because we have more time to find things, we find more things.
All right, we've got a question from online. I'm going to ask it says, is there any neutrino emission from a supernova explosion?
Ooh, that is an interesting and research question. So the answer is there has been. We know of at least one object, supernova 1987A in Large Magellanic Cloud, that emitted some neutrinos. They have to be very powerful explosions. The kind of explosions that create these neutrinos are almost certainly not the type 1a supernova I was looking at, but much more analogous to the core collapse of those massive stars like Krypton exploding, the sun of Krypton exploding. So those sort of events will produce neutrinos. There's a lot of research to try to find these things. There are detectors that are essentially giant vats of heavy water and sodium with photomultiplier tubes all around them, both in Antarctica and Japan, all over the place, to try to find these signals. But we've not been able to find very many of these things. They're really hard to tease out because we also just don't find that many supernova near us. It's probably for the best, really.
Okay.
Go ahead and pass the mic down.
Who's got the...
Given the age of the universe, something 13 or 14 billion years, are there likely to be more supernovae in the future, or is it a kind of steady state throughout?
This is a beautiful question. And that has a complicated answer. The kinds of supernova and their rates change as a function of the age of the universe. So as we go further and further back in time, you expect fewer and fewer type 1a supernova. The universe hasn't had enough time for stars to grow old, die, form white dwarfs, and have many type 1a supernova. But on the other hand, you have more and more massive stars the further back in time you look. And so you have more core collapse explosions. Moving this further and further into the future, the opposite thing happens. You'll expect more type 1a supernovae because the universe is older and you have more of these white dwarfs. And you'll expect fewer core collapse explosions because the universe is just producing less of these really massive stars. But we're talking about changes over billions of years. These are hard to measure on sort of small time scales, like millions of years. So it is really very far in the future that we're talking about where we'll see a significant difference. The numbers of these things that we find are actually quite uncertain. And so this is an active area of study.
Okay. Got the microphone up there?
Hi. I was wondering, do we have any predictive ways of figuring out whether a particular star is going supernova? I mean, obviously, maybe we can be like, oh yeah, in a couple million years, but anything within our lifetimes?
Yeah, so
Oh, sorry. And I also wanted to ask what would happen if a supernova did happen near us, like Alpha Centauri or something.
all right. So are there predictive ways of looking for supernova events? In some cases, yeah. We sort of, if you look up in the night sky today, and you go look at the Orion constellation, you'll see a star called Betelgeuse. Betelgeuse is a red giant star. It'll die, and it's in some point in time or the other. We know it'll end its life as a supernova. The problem is we just don't know when that will be. It might be a million years, it might be tomorrow, it might be several billion years. And this is a problem if you sort of want to write your PhD thesis because you only have a few of these years to do it in. Similarly, people have looked for sort of white dwarfs which are around other systems and look to be sort of in decaying orbits where they look like they might merge and have an explosion, but none of these systems are sort of easily studyable on timescales that are comparable to human lifetimes. So what we do is the scattershot approach, where instead we look in lots and lots of millions of galaxies and try to find what blew up instead. As for what will happen if Alpha Centauri blew up near us, not a whole lot. It's actually pretty far away. So Proxima Centauri is about 4 light years away. You wouldn't really worry about it. You'd see something cool in the night sky for a while, but it's far enough away that it's not a huge impact anytime soon.
You mentioned the subject of neutrinos came up. Is that the reference to IceCube up there?
Yep. So the IceCube experiment has a whole bunch of people at the University of Maryland involved in it. And so we're really excited about these things because they're really a channel of physics that we've not been able to probe easily in the past. We've had telescopes like Hubble and JWST in the future that look at photons, but neutrinos are effectively giving us a different story of physics. And so we're really excited about what we can learn as these facilities like IceCube get more and more sophisticated.
So we've got a question online. I'm trying to paraphrase it. Can we measure a star's rate of decay into a white dwarf, or its transition from stable to unstable?
Can we measure a star?
If we looked at the sun's going to go white dwarf in 5 billion years right now, or whatever. Can we measure the sort of if it's going to go? I don't think.
We've seen stars evolve significantly in very few cases. There are stars that are already in a part of space called the instability strip. And these stars effectively are sort of done burning fuel for the most part. They're slowly moving towards these other phases of stellar evolution, be it a red giant or a white dwarf. And because these things are unstable, they do show pulsations over time. They show all sorts of unpredictable behavior. And so that kind of thing has been studied. But have we seen a single star evolve from burning hydrogen to running out of fuel, becoming a red giant, and then becoming a white dwarf? No. That would be several billion years.
All right. We see the very most massive stars like Eta Car.
Right.
Over the past 150 years, it's had lots of outbursts and such. So the very massive stars, we see things, but the boring stars are kind of boring. Yeah.
Right. Sort of by definition.
Other questions here? I got one up there.
Cool. What kind of things can you predict about stars as the metallicity of the stars increase? And so you start ending up with very massive stars that are going to go supernova, but they've got a lot more metal than the stars in the current era do.
So this is a hard question without getting a whole bunch of stellar astrophysics. Maybe the right answer to this question is that I find you after this talk and we chat, because this is lots of properties of stars change. Their temperature, their surface properties, sort of whether they have sunspots or not. There's so many different properties of stars that are effectively impacted by whether they have just a small amount of metal in them. And so as the metallicity of stars change, lots of different things change at the same time. And it's a really complicated picture to try to explain all of that. But the answer is we see these things. We see it has an impact, which is why we care about it.
So you said that the supernova are the source of many of the minerals in the universe, and the Earth is made of these elements. So do we have any guess when and where from the elements, where the supernova was that produced the elements that comprise the Earth?
Not a good guess at all, right? Our galaxy, our solar system is several billion years old. The Earth is about 4.3 billion years old. Supernovae that would have gone off in our galaxy before that, we obviously can't study and tell you anything about, but they'd have had to happen before that for all of these metals to be around. Now, the galaxy itself has a dynamical timescale. It evolves, it changes, stars move around, and that timescale is much shorter. So there's almost no way to back out effectively what star exploded as a supernova to effectively seed the Earth with its primordial elements. We can't ever tell that. In fact, the last supernova we've seen in our galaxy that was visibly observed in the northern hemisphere was in fact Kepler supernova in 1609 or whatever.
Yeah, and a good thing to keep in mind is our sun has made about 18 orbits around the center of the Milky Way since it was born. Right. So there's a lot of diffusion and things that happens in 18 orbits. And so what was near us 18 orbits ago is not necessarily near us today.
And of course, the galaxy itself is a violent place. Our Milky Way, we've seen evidence of it cannibalizing other galaxies. There's a stream of stars called the Sagittarius stream, which we think is effectively the Milky Way eating the stars off of another galaxy, ripping the matter off of it into our own. And this will eventually happen several billions of years into the future with our galaxy in Andromeda. These things will come to a head, and there will be stars effectively moving between these two galaxies. So these systems are unstable, and we wish we could trace things back that far, but not.
Okay, we've got a couple kids up in the corner. I told them they could have a question if they have. Do you have any questions for us tonight? All right, they don't have any questions. No. I always like, when we get school kids coming, I always like to answer their questions. All right, next month, November 13th, a week after Election Day, Bill Blair will be talking about observing with Hubble, the whole process from the idea through the proposals all the way up to getting your data, processing it, and publishing the paper, okay? Observing with Hubble, Bill Blair, November 13th. Let us give Gautham another round of applause.